In beginning discussions on probability, we have to talk about counting, and before we can talk about counting, we have to talk about sets. So here I want you to look at this information here regarding set notation. Let's start with the definition of a set. A set is any collection of objects or elements written in such a way that we can tell whether any given object is in the set or not in the set. Generally, when we describe sets, we define them as uppercase letters to represent the sets. And the objects that are in the sets are called elements, and sometimes they're called members. So these notations here just show you some symbols that are used with set notation. For example, this symbol here just says that little a is an element of capital A. And so that just means that this element A is in the set A. And if you see the same symbol with a line through it like this means A is not an element of A. So if you considered, let's say you considered the set of counting numbers 1 through 9, and let's say that A was only a subset of those numbers 2, 3, 5, 6, 8, 9, then we could say that 2 is an element of A, and we would say that 1 is not an element of A since 1 is not in A. Now, the empty set is actually a set with no elements in it. And there's a couple of different ways that you can identify the empty set. One is this null symbol here, and another way is just empty set of braces. So consider all numbers rolled on a 6-sided die. So that would be the numbers 1, 2, 3, 4, 5, 6. Then if I asked you to list the set of numbers rolled that are greater than 10, then that would be the empty set, because you can't get a number greater than 10 from this set of numbers 1 through 6. Some other symbols here, this just means that A is a subset of B, and what that means is that everything that's in A is also in B. Now if A equals B, that means that everything that's in A is also in B, and everything that's in B is also in A. So in other words, they have the same elements. And this just means A is not a subset of B, and this means A is not equal to B. So consider these sets here. Let's say we're talking about the counting numbers 1 through 9, and let's say A is the set 1, 3, 5, 7, 9, and B is the set 2, 4, 6, 8. And C is the set 3, 5, and D is the set 2, 4, 6, 8. Now, C is actually a subset of A because the elements in C are also in A. C is not a subset of B, though. So C is not a subset of B. Okay? And then here, I've got a typo here. That should say A is not equal to D. So A and D are certainly not equal, A and B are certainly not equal, and A and C are certainly not equal. And then lastly, the empty set is a subset of every set. So the empty set's a subset of A, subset of B, subset of C, and so on. Now, as I said earlier, when we're describing sets, we generally use capital letters. So, and then also something else you probably need to know is, let me just show you this. Let's say the set of all odd numbers between 2 and 10 is our set, and so that would be the numbers 3, 5, 7, and 9. If you wanted to state how many elements are in a set, you actually use this notation here with a little n with parentheses and the set in the parentheses. So for example, this notation here tells me that the number of elements in set A is 4. And if you go back and look, you can see there's 1, 2, 3, 4 elements in that set. And then here's another example. Let's say the set contains a cat, a dog, a bird, a horse, and a cow. Well, the number of elements in that set would be 5 because there's 1, 2, 3, 4, 5 elements there. The universal set, denoted by U, is the set that represents all elements considered. And a Venn diagram is a visual representation of one or more sets. Now, I have some Venn diagrams on the next page that I'll show you. So let's consider the counting numbers 1, 2, 3, 4, 5, 6, 7, 8, 9. Then the universal set would be all of those numbers 1 through 9. Now, there's two other set definitions I need to talk about. One is the union and the other is the intersection. The union of sets A and B, denoted by this notation A union B, is the set of all elements formed by combining all elements of A and all elements of B into one set. So in other words, we include the elements that are in both sets, but we just include them once, so don't duplicate. So for instance, let's say the universal set is the numbers 1 through 9, and let's say that set A is 1, 3, 5, 7, 9, and let's say set B is 3, 4, 5, 6, and let's say set C is 2, 4, 6, 8. Well, then to define A union B, we would take all the numbers that are in A, 1, 3, 5, 7, 9, combine them with all the numbers in B, 3, 4, 5, 6, but we wouldn't duplicate the 3 and the 5. We would just write them once. So we would end up with 1, 3, 4, 5, 6, 7, and 9. Now if you did A union C, you actually get the entire set of the numbers. You get all 9 numbers, because there you don't have an intersection there. And going back to the notation for the number in the set, the number in A union B would be 7, and then the number in A union C would be 9. Now the intersection of sets A and B, denoted by this symbol here, A intersect B, is the set of all elements formed by listing all elements that simultaneously occur in both sets. So if we go back to our sets we were using in the previous example, A is 1, 3, 5, 7, 9, B is 3, 4, 5, 6, and C is 2, 4, 6, 8. Then A intersect B would only be those numbers that occur in both sets. So like here, you see that 3 and 5 is in set A, and 3 and 5 is also in set B. So A intersect B would be just the values 3 and 5. Now, if you look at set A and set C, you'll notice there is no common ground there. There's no intersection. There's no element that's in both sets at the same time. So in that case, we would say A intersect C is the empty set. And as far as how many elements are in the set, the number of elements in A intersect B would just be 2 elements, the 3 and the 5, and the number of elements in A intersect C would be 0, since there's 0 sets. Below is what we call a Venn diagram. And so to identify the elements that are in the union of two sets A and B, it would be this purple region here that's shaded, and so that represents all the elements in A plus all the elements in B. And then in the intersection, it would be this this purple region here that's in the intersection where the two sets overlap. So this is a visual representation of the union on this side and the intersection on this side. And then the last thing I want to talk about on this video is the complement of a set. The complement of a set A is denoted by A prime. In other books it might also have an A with a bar over the top of it, but A prime is considered to be the complement of the set. So that's the set of elements that are in the universal set but that are not in A. So for instance, if we go back to the same sets I used before for A and B, let's say set A is the elements 1, 3, 5, 7, 9, then A prime would be those elements that are not in A that are from the universal set. So the elements from the universal set that are not in A would be the numbers 2, 4, 6, and 8. So A prime would be that set. And then B prime, B was the numbers 3, 4, 5, and 6. So those not in B would be the numbers 1, 2, 7, 8, and 9. And then the number of elements in A prime would be 4, and the number of elements in B prime would be 5. And then the last thing I want to mention here is that here is the visual diagram of A prime. So let's say this set here that's red represents all the elements in set A. Then notice the green shaded region would be A prime all the elements that are in the universal set but are not in A. In the next video we'll look at some applications of these set notations.